Hello everybody and welcome back to this video on this new part of the course entitled Log and Exponential Functions. So today I'm just going to introduce the concept, and hopefully in the second video we'll be able to use what we learned today into doing some calculus with it. But right now it's going to be a mix of review of high school and also a couple of limits from calculus, so that, like I said, we're going to be ready to do derivatives comes the next video. So, part one, introduction. Let us start this introduction, if you don't mind, with a little definition. What is it that we call an exponential function? So, an exponential function f of x. An exponential function f of x is one where the variable x is a function where the variable x sits in the place of the exponent. That's why it's called an exponential, in the place of the exponent. So if you have like x squared, then the x is in the base. That's not an exponential. But if you have 2 to the power of x, then x is the exponent. That's an exponential. Let's take a look at exactly, as an example, what that function is. F of x is equal to 2 to the x. That's an exponential function. That is an exponential function because x is in the exponent place. It's in the exponent position. What does a function like this look like? Well, let's take a look at the graph of something like 2 to the power of x. The best thing to do here is probably a table of values. So let's pick up a couple of x's and y's. Genre minus 2, minus 1, 0, 1, 2, and 3. All right, so we put that in here. 2 to the minus 2. 2 to the minus 2 is 1 over 2 to the 2 is 1/4. Yep. Minus 1. 2 to the minus 1, that's 1 over 2 to the 1. That's 1/2. 2 to the 0, anything to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. So I guess with these 6 values, we should be able to get a good idea of what the graph looks like. So x-axis, y-axis, x-axis, y-axis. Going to give ourselves a couple of values here, minus 1 and minus 2 and 1 and 2 and 3. And we'll approximate the y's. So minus 2 1/4, very, very, very close to the x-axis. Minus 1 1/2, oh, ever so slightly higher, but not that much. Let's put 0, 1 here. So let's put 0, 1 here. And then 1, 2. And then 2, 4. And then 3, 8. So we got something like this. Let's put it in a different color. It's going to look a little nicer. So going to go like this. And that point is a little off, so we'll bring it back to the curve over here. So you see the shape. Oh, you see the shape. So it actually is almost flat on the x-axis here. As a matter of fact, the x-axis is an asymptote for this function. And then, boom, it actually jumps really, really high this way. So a couple of things about that. What's a domain of a function like this? Domain of f of x What's a domain? What are the x's that we can actually put into the function? Basically, anything at all. Right? The range is only the positive, the range of f of x is only the positive y values, so we can actually put it like this, from 0 excluded to infinity, which is always excluded itself, yes. And what else could we actually put here as an interesting remark? There is also an interesting limit that takes place at negative infinity. If x goes to negative infinity of this function, so x is really, really, really far to the right, the curve leans more and more and more towards the x-axis, giving us a y value of 0. So there you have it. That's your exponential function for you. And yeah, that's pretty much what I have to say about that. So hopefully this is not too overwhelming, pretty easy stuff. And now let us talk about the inverse of that function, which you actually have heard called the logarithmic function. So, definition, once again. Definition. The logarithmic function, is obtained from the exponential function, is obtained from the exponential function, by or when x and y trade places. That's what we call the inverse function, when x and y actually trade places. So basically, let's take a look at what happens. So example, recall the little table of values we had for y is equal to 2 to the x. Now let's switch. Let us switch. Let us switch x and y in the table of values for y is equal to 2 to the x. So remember what we had here? It's actually fairly simple. We gave for the x values, we gave the values -2, -1, 0, 1, 2, 3. Well, then we switch the x and the y. So the y values, they become this. Right? And what were the y values now become the x values. So we have here 1/4 and 1/2. These are the y values of the exponential that now become the x values of the something we're going to call the logarithmic function in a minute. So 1 and 2 and 4 and 8. What kind of a graph are we going to obtain from that? What kind of a graph are we going to get? We are going to get something like this. Here's an x, here's a y, and let's give ourselves a couple of quarter. So say, I don't know, say 1 is here, say 2 is here, 4 and 8 are far on the other side. So if x is 1/4, very, very close to 0, then the y value is -2. We could put it maybe just down here. And then if x is 1/2, and -1, so 1/2, maybe -1, and 0, and 2 and 4, we're going to get something like this. So 2, 4 would be here, and this would continue and continue and continue going down like that. Let's call that f of x. Let's call that f of x. Yeah, so that goes on forever. And then basically you can see here that the domain and the range of each one are, well, the domain of the exponential is going to be the range of the logarithmic. What's a domain of this function? Domain of f of x. The domain are the x's that we are allowing into the function. So nothing until 0, and then the domain begins at 0. So it's 0 to the right. So I'm just going to put a verb here. So from 0 to infinity, and you notice that was actually the range of the exponential. The range of f of x, the range of f of x, so the range is all the y values that go in there is r. And just like, what do I put like a dot here? It's not IR, it's r. And remember that the exponential had a limit as x went to infinity? Well, this also has an interesting limit, except that it's approaching 0 from the right. What is the limit as x approaches 0 from the right side? The graph plunges to negative infinity. Good. Good, good, good. That type of a function is actually called a logarithmic function. This is the graph, of a log function. In particular, this is the graph of f of x is equal to, okay, I'm going to introduce the notation. You have seen that in high school. LOG for log, so the log of x, and I'm going to put here the base 2. That function, which is represented here, is written as f of x is equal to log base 2, with its domain from 0 to infinity and its range all of r. Good. So that's just a quick little intro on logs. We're going to get rid of this. All right. So what shall we do next? We shall actually take a look at the following thing. What we have seen is if we actually switch the x and the y. So when we switch x and y in the exponential function, y equals 2 to the x, we get what happens when we switch the x and the y here. Well, we get x is equal to 2 to the y. The graph of this, corresponds, like we said in the previous whiteboard, corresponds to y is equal to log to the base 2 of x. So that's what I want to point out. X equals 2 to the y will give us, when we transform it into a log, y equals log of x to the base 2. That's your basic transformation formula. So this is your basic transformation. When you want to change an exponential to a log, this is what you do. Okay? So basically, it's the same thing. If I have, for example, something like 8 is equal to 2 to the 3. Now we all agree, right? 2 times 2 times 2 is 8. That is exactly the same thing as 3 egal log base 2 of 8. Right? So this is how you do things. I personally remember it by doing the following. I take the base of the log, raise it to the power of what's on the other side, and it gives me the answer that is inside the log. So 2 to the 3 inside the log is equal to 8. Similarly, what could we get here? What about something like 25 is equal to 5 squared? Would you be able to change this into a log? Not very difficult, yes? What do we say? We shall say that 2 is equal to the log base 5 of 25. And once again, you can verify this by taking the base 5, raise it to the power of 2, and what you're going to get is the answer 25, right? So ballpark, that is what we want to do with the log. Now, this function of ours, this log, has a couple of properties that are interesting. So briefly, again, this is what many of you have seen in high school, but my experience is that, well, high schools are not created all the same. Some people cover this very quickly, some other people cover this in a lot of details. So it's not too bad of a waste of time to just take a quick look at the properties of the log function. Properties of the log function. There's a couple. They're not all equally important. Like the first one, log of a product. Log of x times y. This is known to be the log of x plus the log of y. Okay? You will notice that I'm not putting any base for this. I'll actually tell you why in a second. I just want to expose the 4 property here without any base for the log. Hiya, log of x over y, a division. Well, if the multiplication turns out to be the sum of logs, a division, it makes kind of sense if you think of exponents. It's going to be the difference of the logs. Remember that a log is just the inverse of an exponential. So all these rules can actually be proved using the laws of exponent that we know so well. Now, here's one. I'm going to put a star next to this, because this is the one we're going to use the most by far. When there is an exponent to the x, here's what you can do. You can bring the y straight in front of the log. I'm going to put a star right away before I forget, because that is important. Important. Alrighto. And then there's another one, which is more like computational, which is like, like calculator sort of thing. The log base a of x is equal to the log of x over the log of a. And now, because I've left all of these logs without a base, I know some of you remember, right? So a couple of remarks. What is this log with no base? Log x with no base corresponds to the log, base what? You know this, yeah, base 10, absolutely. And then there is something called, and I'll come back to this in a moment, log base, Okay, this is where we have to spend a little bit of time talking about this guy, E. Okay, I'm just going to leave it like E for now, but as soon as we get rid of all this, I'm going to talk a bit more about this very important number, both in science and in the social science. Log base E, this is known as ln. So we're going to meet this guy a lot in this chapter, ln. But when you see ln, I would like you to think of this as log base E. Okay? So log no base is like log base 10. All right? And log, or ln should I say, is like log base E. Keep that in mind. And we will now ponder a little longer on what this number is and the role that it actually plays in calculus. So let me get rid of all this and let's talk about the number E. So about the number E. E is an irrational number. It's an irrational number. What other irrational number do you know? Pi. Yeah, it's exactly in the same family as pi. Irrational number, and its value is 2.718 blah blah blah, just like pi is 3.145 blah blah blah. Right? We'll come back quickly on the value of E in a second. E is the first letter of, I wouldn't say its inventor, but the first mathematician actually who kind of paid attention to this number, of Leonard Euler, a Swiss mathematician actually, who was the first one who looked at that number. So E for Euler. So basically, where does it come from? Where does E come from? What was the investigation that actually led to the discovery of this strange number that has so many applications everywhere in mathematics? It actually comes from a limit. The limit as n goes to infinity of 1 plus 1 over n to the power of n. If you take a look at this limit, and the way we learn it, the first thing we do with a limit is you cheat, is you replace n by infinity in here. I mean, this actually will give you 1 plus 1 over infinity to the power of infinity. Now we all know that 1 over infinity is 0, so that should be 1 to the infinity, which can be interpreted at a very naive level as 1 times 1 times 1 times 1 forever. So shouldn't it be 1? It actually isn't. Because if you make a table, and that's pretty much what Euler did with his students, so here's 1 plus 1 over n to the n. We're not going to like go deep into that, but if you just like take n is equal to 1, then 1 plus 1 over 1 is 2, 2 to the 1 is 1. If you take n is equal to 2, and 1 plus 1 over 2 is 1.5, 1.5 to the power of 2 is 2.25. We're not close to 1, and from here to here, we're moving away from 1. Now, we're not going to go through all this. We don't have the time, and it's not the purpose of this lecture to do that. But if you take a very, very, very large number, like say 1 million, and you put it into there, you can verify this on your calculator. 1 plus 1 over a million to the power of million, this, strangely enough, turns out to be this number. And if you take not a million, but 100 million, it's still this number. So as n goes to infinity, this number actually goes to E. Yes, And the e is that number that is irrational, so infinitely many decimals and never any repeating sequence. That's the origin of e. Now, basically, why is e important for us? So e matters. E matters because of, for us, a very special limit. Not this limit. Not this limit. This is the limit for the origin of e. I have another limit that I would like to investigate with you, and it's this one. It's the limit as x goes to 0 of e to the x minus 1 over x. This is a very important limit for us that we're going to be using in the next video. So just laying the ground for the next chapter. Cheating on this, I get 0 over 0, which you remember is indeterminate. Now, there's no easy way to actually crack this limit to know exactly what it is, except doing the numerical value. So numerically, I am going to have a little bit of a table like that. Let's remember what the numerical method is about. So what's the numerical method about? We actually put the target point right here. And then we take on either side the first whole number that we encounter. So minus 1 here and 1 there. And then you actually get closer and closer. So minus 0.1 and minus 0.01. As for the other side, same thing, mais positif. So 0.1 and 0.01. So let's fill this in. Let's fill this in and see what we actually get. If you put in minus 1, you are actually going to get, right here, different color. If you put in minus 1 into here, you're going to get something called 0.63. If you put in minus 0.1, you're going to get 0.95. And this one is 0.995. So you can look at the progression here and most likely conclude that the limit as x approaches 0 from the left of this function, I'm going to put f of x for short, that is really getting close to what value? To 1. So here at 0, I get 0 over 0. And as for the other side, if you put in 1 here, you're going to get 1.72. And if you put 0.1, you're going to get 1.05. And if you put 0.01, you're going to get 1.005. So looking at the transition, you're getting closer and closer to 1, yes? So limit as x approaches 0. This time from the right, that is equal to 1. So my conclusion for this, and it's going to be pretty obvious because the left limit is 1 and the right limit is 1. So limit as x approaches plane 0, no direction, of e to the x minus 1 over x, that limit is equal to 1. We are going to start our next video with this very limit. So that's my introduction to exponentials and logs. It's very succinct. It doesn't go into a lot of details, but it uses exactly what we need to know, the minimal amount of knowledge we need to know to get into the actual calculus, the derivative of all these functions. So that's it for me today. I will see you in the next one. You take care. See you soon. Bye-bye.